In part 4, we learned all about the depth buffer, and in part 5, we are going to write some vertex displacement effects and learn about tessellation shaders. I'm going to jump directly into writing a sine wave shader, so I have duplicated the alpha blended transparency shader from part 3 and named the copy waves. Most of our focus so far has been outside of the vertex shader, but there's plenty that we can do here. Fragment shaders can't physically move a mesh, so we'll need to do that within the vertex shader. To start, let's add a couple of new properties. The first is a wave height, which will define how high or low the waves can go along the y-axis. We can make it a range variable if we want to have a nice slider in the inspector, and we can give it a default of something like 0.25. The second is called wave speed, which will define how quickly the waves roll over the mesh. This one can also be a range variable, although it can probably have a larger range than wave height. Remember to redefine both variables in the C buffer, both of them are floats. Jumping down to the vertex shader function, let's remove the line for position CS for now. First, let's get the position of the vertex. I want this position in world space rather than object space, which will make it so that the waves roll over the mesh based on its position in the world. We'll be able to tile the mesh many times and the waves should connect seamlessly. For that, I'll use a function called transformObjectToWorld and feed in the position OS from AppData. Next, we need to work out how high the waves are at each point on the surface. I'm going to create some basic sine-shaped waves, so nothing too fancy. For that, I can use the sine function and pass in the x component of the position added to the z component. By doing this, the waves will roll diagonally over the surface. I will also add the time to this value, so the waves will scroll automatically. And we can multiply the time by wave speed, so we can control it with the property we added at the start. The sine function will always output a value between -1 and +1, so we can multiply its result by wave height. This line now gives us a value between minus wave height and plus wave height, which we can use as a height displacement value. Let's create a new position variable, which is the same as the position ws we created, but with the displacement value added to the y component. We can now pass this into a function called transformWorld2hClip for the position CS output. It's similar to transformObjectToHClip, but since we're inputting a world space position, it's important to choose the right function. In the scene view, if we assign this material to a plane mesh, then we'll be able to see the waves in action and play around with the wave parameters to make them larger or faster if we want. However, you may notice that some of the peaks look awkward and jagged, which isn't ideal. There are a couple of ways to fix this. First, we could just use a mesh with more vertices. This works fine visually, but you might need the lower poly version in some cases, so you'd end up cluttering your project with multiple versions of the same mesh. And you'd always have to process every vertex when drawing, even if the mesh is far away, which can be slow. It would be ideal to start with the low poly mesh and increase the vertex density on the fly. Luckily, the second approach can do this. The basic graphics pipeline that I presented in part 1 was like this. You start with mesh data, you apply the vertex shader to that data, the vertices are rasterized into fragments, and you run the fragment shader on those. But there are optional stages that I left out, including tessellation, which happens between the vertex shader and the rasterizer. Tessellation happens across a handful of new stages which are responsible for taking the vertices output by the vertex shader and creating new vertices between them. It's pretty technical, so let's go step by step. This might be stretching the definition of basics a bit, because tessellation shaders are very terminology dense, but you can skip this half of the video and come back later anytime you want. Part 6 will be all about lighting, which might interest you more. You can modify the waves shader directly if you want, but I'm going to work in a copy named Tessellation waves. First, let's add some new properties. We'll need a tessellation amount, which defines how many subdivisions to do to our existing mesh. How many times we insert a new vertex between each pair of vertices. I'm pretty sure that the hardware limit here is 64, which is way more than you'll ever need, so let's make that the maximum range for this parameter. I also want to make it so that the number of subdivisions decreases if we move the camera far away. If we're always using maximum tessellation, even far away, then we won't see the benefit, but it'll still be a drain on resources. With that in mind, I'm going to set up a tessellation fade start distance, which is when the amount of tessellation starts to drop from the value we set for tessellation amount, and a tessellation fade end, which is the distance where the number of subdivisions falls to 1, which is the same as doing no tessellation. Remember to define all three of these variables inside the C buffer too. They are all floats. Next, let's talk about the structure of our shader. We will need the appData struct to input data to the Vertex shader as usual, but the Vertex shader isn't going to be passing data directly to the fragment shader this time. Instead, it's going to be sending information to a tessellation stage called the hull shader. This hull shader is responsible for sending vertex data to the tessellation stage, and it accepts a patch of vertices. This is a primitive type like a triangle or a quad, although I'll just use triangles. Then it outputs triangles one at a time to the tessellation primitive generator, which spits out new vertices. So that means our vertex shader will output a new struct called tessControlPoint. This control point will contain a position in world space, and this time the semantic is called internal tessPos. We'll also pass a UV to the hull shader, but we can use the regular text_0 semantic for that. With this struct set up, let's rewrite the vertex function. Its return type will be tessControlPoint, and we can create a new instance of that struct at the start. Then I want this struct to contain world space positions, so I'll use the transform object to world function for that, and I'll use the transform text macro for the UVs. So far, things are looking quite familiar. Next, let's look at what the tessellation hull function does. First, it's going to be outputting instances of tessControlPoint, so that can be our return type. It's going to accept an input patch of 3 vertices. So we specify the type of each vertex, which is also a tessControlPoint, and the number of points here. It also accepts an ID, which specifies which of the 3 vertices we're currently operating on. So essentially, for each triangle, this whole function will be run 3 times, once for each vertex in the triangle. But it will also know about the other 2 vertices in the triangle. Inside the function, all we are going to do is return the current vertex, which we get from the patch. Most of the behavior of the whole function is driven by attributes that we write above it. There will be 5 of these, so let's go through them in order. First, we have the domain attribute, which tells Unity what kind of primitive to use for each patch. I'll use tri for triangles, and I think it's safe to assume meshes you're working with will use triangles too. But the other possible values here are quad for quadrilaterals and isoline for thin lines. Next, we have the output control points attribute, which determines how many vertices we output to create each new patch. Since we're working with triangles, I'll say 3. Then we have the output topology attribute. In Unity, a triangle is defined in the mesh data as a list of 3 vertices, and the order of those vertices matters, as it defines which side is the front or the back of the face. Conventionally, when vertices are in a clockwise order, that side is front-facing, so we specify triangle underscore CW for this attribute. For counterclockwise winding order, you can say triangle underscore CCW, and for isolines, there is no front or back face, so you should say line. Next up is the partitioning attribute. Using integer means that the number of subdivisions always snaps to an integer amount, so there's always an equal spacing between newly generated vertices. But we can say fractional underscore even or fractional underscore odd to allow tessellation without uniform spacing, rounding the number of subdivisions to the nearest even or odd number respectively. You get smoother transitions this way, but one strip of faces will periodically look much thinner than the others. You can supposedly also say power 2 to snap to the nearest power of 2, but this seems to do the same thing as integer on my end. Lastly, we have the patch constant func attribute, and this one is probably the most important of them all. So far, we haven't said anything about how many subdivisions to perform, and that's because we do it in a separate function, which, as you guessed, is called the patch constant function. This function accepts the same input patch as the whole shader, and it outputs data about how many times the sides and inner parts of the triangle should be subdivided. For now, let's assume that we have created a function named patch constant func and put that as the value. Before we get ahead of ourselves, let's think about the data that this patch constant function outputs. As I just mentioned, we need to specify the number of subdivisions along each edge and for the middle. We can package these values into a new struct called test factors. The edge subdivision factors will be a small 3-element array, and the semantic is sv underscore test factor. For the inside tessellation factor, the semantic is sv underscore inside test factor. Now we can write the patch constant func. Its return type is test factors, and as its only input, it takes in the same patch as the whole function. But this function runs once per patch, so we don't get an ID too. At the start, let's initialize the test factors. The easy way to write this function is to just set all 4 tessellation factors equal to the tessellation amount and be done with it. But I wanted to implement the distance-based fadeout that I mentioned before, so this function ends up a bit more complicated. Instead, we'll calculate the distance between the camera and each edge midpoint, and then fade out based on whether that distance is lower than the tessellation fade start, between it and the tessellation fade end, or higher than both. First, let's get the positions of all 3 vertices in the patch, and then, from those values, find the positions of all 3 edge midpoints by taking each pair of vertices and finding the average point halfway between them. Next, we can get the world space position of the camera by accessing a variable called underscore world space camera pos. Then we can use the distance function to find the distance between the camera and each of those 3 edge midpoints. Next, we need to normalize these distance values to the start and end fade range. I want it so that the output is 1 when the distance is less than tessellation fade start, 0 when it is above tessellation fade end, and between 0 and 1 when the edge distance is between those properties. Here's some code that does that. Essentially, if the distance is lower than tessellation fade start, then this part of the expression comes out negative. If it's above tessellation fade end, then it will be above 1. We use 1 minus to get the values running in the correct order, and we pass the whole expression into a saturate function, which clamps all values between 0 and 1 like we wanted. Now, using these values, we can set the edge tessellation factors. We'll just take that normalized value and multiply by tessellation amount to get a smooth fall-off from full tessellation and none at all. I'll make sure that this is always at least 1 by using a max function, else parts of the mesh can actually disappear if this evaluates to 0. For the inside tessellation factor, we can just take an average of the 3 edge factors. You can set this to any value you want independently of the edge factors, but I think this is probably the most sensible approach. We're almost there. The results of both the hull function and the patch constant function will be passed into the tessellation primitive generator, which will produce entirely new test control points, or vertices. Our final job is to take those patches and construct new vertices to pass along to the fragment shader in a stage called the domain shader. This will operate on every new vertex output by the tessellation stage, and its purpose is to attach data to those vertices. Currently, these vertices don't know anything about their position or UV coordinates. The tessellation primitive generator just says, here are some new vertices, and this is the patch I generated from. You figure out what data to attach to them. Since this domain shader connects the tessellation stage to the fragment shader, I will rename the v2f struct to t2f for tessellation to fragment. It contains the same clip space positions and UVs as before, and is going to be the return type of the domain function. It takes in our test factors struct from the patch constant function, our output patch of those 3 vertices from the hull shader, and a set of special coordinates called barycentric coordinates, which tells us how far this vertex is from the vertices in the output patch, as a set of weights that sum to 1. A point with coordinates 1, 0, 0 lies exactly on an existing vertex. If the coordinates are 0.5, 0.50, then this is the midpoint of an edge between 2 existing vertices. And if the coordinates are 1/3, 1/3, 1/3, then this point is exactly in the middle of the triangle. It's worth noting that if you were using quad topology, this coordinate would be a float 2, which would act more like a conventional UV coordinate. Essentially, the domain shader takes the data from the 3 output patch vertices, which is known data, since we just pulled that data from the vertex shader, and uses the barycentric weights to interpolate between that data and set it on the new vertices, which have unknown data to start off with. We can set up the t2f struct at the start of the function, and then we interpolate the world space position between the 3 patch vertices by taking the position from each vertex and multiplying by the corresponding barycentric coordinate, then adding the 3 values together. We can do the same for the UVs. Take each patch vertex UV and multiply by the barycentric coordinates, and add them together. So far, we haven't done anything wave-like in this shader, and since this is the first time we truly have access to the new tessellated vertices, now seems like a good time to do so. We can use essentially the same code as before. Calculate the wave height with a sine wave based on the xz position and the time, add the offset to the position y component, and then pass this new position into a transform world to h clip function to set the clip space position on our t2f struct. We can also set the UV on the t2f instance here. We also need to add one attribute to the domain function, and it's the same domain attribute as before, with the value try. There are a couple things remaining to be done. First, make sure that the fragment shader takes in a t2f instead of a v2f as its input parameter. Then, at the top of the HLSL program block, alongside the other pragma statements, we can say pragma hull hull and pragma domain domain to set the names of the hull and domain shaders respectively. Even though we used very obvious names for each, Unity still doesn't treat them as special in any way. Returning to the scene view, if we use this shader on our mesh instead, And we should see an improvement in those jagged bits of the wave if we crank up the tessellation amount a little. Obviously, there's a point where it stops being worth it, so it's up to you to set the right level of tessellation to get a nice looking result without using too many vertices. I once mistakenly handed a client a shader with maximum tessellation on all the time, and it didn't take long to identify why we were in single-digit frame territory. We can also see the fade out if we move the camera back a little. When you're this far away, those jagged edges matter much less, don't they? We can probably go even further and replace the original plane mesh with a simple quad, which lets us get even fewer vertices at far distances if we want. This tutorial about vertex displacement mostly turned into a tutorial about tessellation, but either way, I hope this taught you a lot about the graphics pipeline. In the next part, I'll be adding lighting to our shaders, and we'll explore how to get information from lights and apply them to objects. Until next time, have fun making shaders.